So, yeah, if we have the case holds for all functions of lesser complexity than this and than some particular f, we want to show that also the graph of this function is in dm plus 1 if we say that it has m arguments. So, we assume that each one of these terms, each one of these terms has lower complexity, and so we know that the theorem holds for it, that for each one, it has some number of arguments, and its graph is in dni, right? Whatever its length of arguments is. And so, or I guess that should probably be dni plus 1. Anyway, from the second clause, we have that for every function symbol, its graph, right, the associated function and its graph are in dm plus 1. Now, it might almost seem as though, well, isn't this just the whole point, that the graph of the function is in dm plus 1? But no, because the terms inside of the function are of length n, and they map to certain values that then f maps. So in fact, this is not exactly the thing that we're trying to prove. So, to deal with the terms inside as functions, then we sort of construe the term function for each one of these, the term function for f is the graph where we first map the terms to some element in the domain, and then map those values of the terms to, we evaluate them in f. But having re-expressed all of this in terms of some formula using basically conjunctions, the closure rules, right, the rules about having being closed under intersection, union, and complement, right? If I'm basically just conjoining a bunch of constraints, this is like taking intersections of things that for which the graphs we know already exist, and so by the closure rules for intersection, we know that whenever I express things in terms of conjunctions, that in fact this will be in the appropriate set D. So at this point, just using the fact that these were conjunctions in the closure rules, we get that the graph of the function is actually not in dn plus 1, but in some x that is in dn plus 1.